Assalamu alaikum wa rahmatullahi wa barakatuh. Good evening to everyone. I'm honored today to welcome you to our meeting. My name is Yasser Wafia and I'm a member of the Electrical Engineering Students Club. Today I'll have the pleasure to introduce our guest today who will be talking about an interesting topic, which is robotics. It's an important and interesting topic because some repetitive tasks that are performed by human beings uh, today, but in the future, these tasks will no longer be done by human beings, thanks to robotics. Our guest, Dr. Mohammed Bilal, has retributed in the World Robot Olympiad back in 2019. He worked as a PhD researcher in KAIST, South Korea. He is currently an associate professor in electrical engineering in King Abdulaziz University. So, without any further ado, please welcome our guest, Dr. Mohammed Bilal.
Assalamu alaikum warahmatullah. Thank you for the introduction. We have a very limited time today. Within 1 hour, we have to finish up, and there are a lot of things to discuss, a lot of things, exciting things. I am personally quite find this topic fascinating. And I hope that by the end of the lecture, many you would also have many questions in mind, and we could have a meaningful discussion there. So let's get started. Now, the first thing that may come as a surprise to most of you is that the robots are not an entirely new idea. So, for example, as long ago as 1720s, people had been making robots. Of course, those were not electrical robots; were mechanical ones, but still they were quite fascinating, quite marvelous robots, and they did the job that they were intended to do. So this particular robot, for instance, this was designed to mimic human handwriting, and it was made by this Swiss watchmaker. So watches, they are Swiss watches. The Swiss watchmakers, they are famous for making very precise and very complicated watches. So, and since long they have been famous for that. So this watchmaker, he made this robot, which was back then called an automaton, and it was used by some bankers for automatic signatures. So it was fully programmable. As you can see inside, the programmability comes from the gears, which were set in a certain way so that this robot could write or, or do certain signatures. So you change the gears and an entirely different signature could be done by this. So such an early system and worked precisely. And one other thing that you could notice here is that although the purpose of this robot is to only write something on the paper, and yet this was made in the form of a human. So this is a full human length, human size robot. And although they could have done the job by just building this hand, so the thing is that humans, they are also fascinated by the idea of having a full human sized robot or someone that could help them with their tasks. So this is the fascination. This is why although in our industry, you see, if you go to the industry, there are many mechanical robots and they do the job and they do it very efficiently. So we probably don't always call them robots. We just call them the machines. And so they do the work exceptionally well, but still we want our machines. So the future machines, we want, or we perceive them to look like humans. So that is the fascination with the robots. So whenever the name robot comes up, we think of a machine that looks like a human. And this fascination has been reflected a lot in the science fiction. So if you have been following the media portrait of robots, so you could notice that there is a trend of robots mimicking humans as much as possible. So for instance, back in 1977 in Star Wars, the R2D2, which was an intelligent robot, but it did not look like a human at all. And then gradually we see the robots becoming more and more human. So for instance, Terminator 2 in 1991, although it looked like a human, but it was exceptionally powerful, very intelligent, and of course, it looked like a human being. But we still thought that maybe something is missing, and that's why in Ex Mechanica, which came out in 2015, the robot was actually disguised as a human being. So by the almost till the mid of the movie, the people who were watching the movie, they could not guess which is the actually human and which one is the robot. So that's the fascination, making a robot almost real life, and there should not be any you could not even distinguish between whether the person, this is the real person or this is a robot. So that's the fascination now, and that happens when you incorporate a lot of intelligence inside. So although Terminator is a lot powerful, and R2D2, it could even fly spaceships, but we did not settle with those. We want an actual human-like robot. And that's why you may have, if you have been following the news, you know, the Sophia robot, the entire purpose of this robot is to hold conversations and express human-like emotions and so on. But of course, this is one dimension of the robots. On the other hand, you may have been following the works of Boston Dynamics, which has now become world famous for their exceptionally agile and intelligent robots. So again, these robots, although I would not call them exactly intelligent, they are, however, very agile. So they can work in various terrains, and they can work indoors, outdoors, in difficult terrains, and so on. But they are not, you could say, that much intelligent, although a lot of different type of intelligence goes in there. So that's the purpose of this talk today. That, I mean, in the not only in just in the media or in actual world now, we see quite sophisticated and very difficult, seemingly difficult to make robots. So what else remains for us as engineers? Can we still do something about it? So the answer is yes, because these robots, they are highly specialized robots, and you would not want either of these robots to be in your homes, for example. So in your homes, you would want something to help you with your kitchen tasks, for example. So none of these robots is suitable for that. Our homes are messy, they are disorganized, and they have different obstacles like carpets or stairs and all. So these robots, they may actually not function that well in our homes. So seemingly some dumb robots, if we want in the future, we want robots to actually help us with our daily chores. So for that, we will probably need some very dumb robots as well. So they may not look like humans exactly, but they may help us with a specific task. So that's the purpose of this talk: how to make robots that could help us in a given function. So for that, we need to look into the skill set that is required for this thing. So the very basic of them, we have already seen that the automaton, which was a mechanical one, it could move. So the name robot actually triggers the word motion. So if something could move, only then it could be called a robot. So motion is must, of course. So the most basic of these things is motion, and in engineering we call it actuation. So the machine that you would like to call a robot, that should do some actual work, and it will do that work through actuation. And then on top of that, when we want that robot to be to look like intelligent or do some task in an unsupervised load without a human being controlling it, so that would be adding some sophistication on it. And for that, of course, we will need the robot to sense its environment, and then control according to certain criteria, and then also do some tasks. So we will inshallah look at these things step by step. And then on top of this everything up, so even if your robot does a lot of things automatically, you may also want it to do certain more intelligent tasks. So for that, these days, we will also see in this talk later on, inshallah, that computer vision and AI or machine learning, it has now started playing an active role in that. So in recent era, images and videos, they have sort of become the primary sensor for many applications. So that's why whenever the word artificial intelligence is mentioned or intelligence is mentioned, so automatically computer vision, or with this vision, images and videos, they automatically are considered to be understood that this intelligent machine or intelligent robot, it must be using images or videos in some way. So finally, we will end this talk, inshallah, with some case studies, some local case studies, how we put together some robots that could do certain tasks. Of course, they were not as sophisticated as the ones you see in the media, but they could do certain things, and they could do certain things quite intelligently. So let's start dissecting the robot. As you mentioned already, the most basic thing when discussing robots is, of course, the motion. And when it comes to motion, there could be multiple types of motion. So for example, a simple car going from A to B, it would only require some simple rotational movement on its wheels. But if you are interested in making a robotic arm, then you would want multiple motors to act in synchronicity with each other so as to do a certain task. For example, in printers, you would want the inkjet or the laser jet to move to a very precise location. So that is only possible if you have multiplicity of arrangement of motors, which they are doing very precisely. And same is the case for maybe prosthetic robotic arms. And in the industry as well, in the industry, however, your goal would be to carry heavier loads, but not just carry loads, but also do it with some precision. So you would want a particular component which is heavy to be moved along a certain path, going from A to B in a certain way. So each of these motions, they require a different set of motors. So of course, the most basic of these is the DC motor. When you attach gears to them, so that gear part, as engineers, I'm guessing you already know that gears, when you attach them to a basic motor, it gives the motor an additional torque. So in most of the cases, you saw that torque is an important thing. So the most basic amendment that you could do a simple motor is, of course, you could add some gears so that you have additional torque. And then you would also want to do some very, very basic controls. So for example, you would want to change the speed of the motor, and you would also, of course, want to change the direction of the motor. So all of these things, they have been sort of matured right now. So maybe some 30 years ago, or in 80s or 90s, maybe doing a project on robotics, that would have been a very expensive hobby, or that would require collecting things that must be imported from some very specialized location. But these days, thanks to the advancement in power electronics, and not just power electronics, but also the way we now build motors and all. So this has improved a lot in the last 20 or 30 years. So now we have plenty of things, plenty of devices, ready-made devices available that help you build your robots real quick. And the speed control or the direction control, these are now considered the very, very basic things. So just for your reference, if someone is interested in building a simple speed and direction control circuit for a simple motor, so this is a very commonly used power electronics circuit that electrical engineers very commonly used in their projects. So if someone is looking for building a very quick and dirty robotics project where you want to change the speed and direction of it, so this is what you should be looking for. Then once you have done the basic movement, then you would want to maybe do it precisely. Maybe you would want to move the motor by a certain degree or by a certain distance. So for that, we would require what we call the position encoder. So inside the motors, After we have added the gears to add torque to it, so now we would want to measure the position as well. So for that, we add what we call the position encoders. So again, thanks to the advancement in the industrial technology, motors with position encoders, they are very freely available, very cheaply available, and you could control not only their speed and direction, but you could also read at what distance exactly they have traveled, how much angle uh, in either direction, clockwise or anti-clockwise, they have moved or you would want them to move. And then you could control their speed through what we call the a very famous, very popular method, which is the PWM, pulse width modulation. So I truly wish we could go into the further details of it, but since the topic is right now is the robotics in general and not the motor control or power electronics, so I will not go into the further details of it, but of course you are welcome to search more into this area. Now, thankfully, using the same methodology, which is pulse width modulation, we could also control a second type of motor, the type of motor which goes back and forth. So, for example, if you notice the behavior of this motor, it can move by a certain angle. It doesn't continuously rotate in either direction, clockwise or anti-clockwise, but it moves by a certain angle, and the angle is controlled through, again, this a similar kind of signal, which is pulse width modulation. So we call these motors servo motors, and this is the kind of motors that you would hook up inside a printer, for example, for precise movements, and also in industrial robotic arms. So generally, if you want to build a robotic arm which can have certain types of movement, but not exactly rotary movements, so then this is the type of motor that you should be looking at. So you can notice that your actual arm, your knees and your elbows, they all actually move something like this. We cannot move our knees or elbows, we cannot rotate them, but we could do something like this. So you could say that this is so using this you could make or mimic a robotic arm very easily, and they can be quite strong. They can have a lot of torque as well. So again, you could get very easily get from the market some very small servo motors as well as very large ones which could carry a lot of weight as well. And then finally, the last type of motor is where you want extremely precise motion. For example, in a printer. So in printer, so although the servo motor that we just discussed, it could also move precisely, but the main purpose there is carrying some heavy weight, and the purpose is not exactly too precise. So that is precise, but not this much precise. So these types of motors, which are inside the printers, 3D printers, as well as your normal printers, they are very, very precise. They can move in the order of millimeters. So they could move by 1 millimeter in either direction very easily. But of course, then the downside is that they are not very, they cannot carry a lot of weight. They cannot provide you a lot of torque. And their control is also a bit more complicated. But again, as I mentioned previously as well, the control and the electronics for all of these power electronics and these things for these motors, they have now matured to the point where you could just buy most of the control very cheaply, and they are very commonly available. And things like this, for example, even some 20 years ago, getting your hands on a stepper motor, that would have been difficult. Getting spare parts for your printers, that would not an easy task. But nowadays, these things, they are considered petty electronics. So every store, even in Jeddah, you will find maybe dozens of stores where they sell these parts. And if you want to hook them up to your own project, you could buy that. And not only that, the electronics and the associated software, maybe, that is also very easily done. So a lot of tutorials out there and a lot of help out there. So you could say that the very basics of the robot, which is the actuation part, thanks to the advancements in both machine technology and the electronics, this is now within reach for most people, and people with even very meager backgrounds in engineering or maths. or sciences, they can build ordinary robots real quickly and without much difficulty. So these are the three basic types of motion that we have just discussed. PWM servos for precise motion, but with also some torque. Stepper motor for very, very precise motions, but not a lot of torque. And gear motors where you can have a lot of torque as well as a lot of speed. But these are, and they can also be moved precisely, but not as precisely as steppers. So depending on your application, you would want to choose an appropriate motor there. Next comes the topic of the sensors, because of course, once you are moving your robots, so you would now want to also do something more, something slightly more intelligent. So when we talk about intelligence now, so then automatically sensors come in. So the most basic of the sensors that you could probably, you might have already used that, or that you may have maybe read about it, is the distance sensor. So again, these are very commonly available. These are the sonars or the ultrasonic sensors, and they work on the basis of the echolocation, and they work very nicely for most indoor environments. They can help you judge the distance from various obstacles, but of course they have limitations. They do not work for obstacles that are at an angle, and for certain soft material, for example clothes and all, they do not work really well, but otherwise they are pretty good at judging the distance between different obstacles. So imagine putting this on the front of the robot, and you get a fairly good idea of where the obstacles are. And by the way, these are the same sensors that are found on the bumpers of most cars. So those distance sensors, they are basically nothing but these sonars. And then you could also have light sensors. They have been actually around for, again, a lot of years, and electronics has matured a lot to be used in a variety of projects. So you could have them there. About the position, we have already discussed that your motors these days, they have position encoders built into them, and you can get a fairly good idea of where your motor, or how much distance your motor has traveled. But if you are outdoors, so there is another very precise way of determining your position as well as speed, and that is the GPS. So if you are outdoors, then GPS is probably your ultimate tool for positioning and also for speed as well in most cases. But if you are indoors, then of course there is no GPS, and this is where the problem lies. So for the robots, indoor positioning is still a challenge, and a lot of work is still being done. And next comes the image, and we have already discussed that in this era, images and videos, they have been sort of, you could say, they have occupied the centerpiece. They are now the centerpiece of our research on robotics, because once you have the images, you will find out that they can be used for positioning, as well as they can, of course, they can act as a light sensor, and they can also be used to measure distances. So you could say that once you have a camera on your robot, it can actually replace a lot of sensors, and it can do a lot of things alone. Even so, most robots, you may find that they do not have any other thing than just a camera. So that's what makes it interesting. And of course, in a supervisory role, you would want a microprocessor there. So even if the microprocessor is not doing a lot of intelligence, at least it is there to do some very basic controls or communications. All right, so if we talk about so we have seen that motion is probably a done deal. You could you could control a motor, you can control it precisely, you can tell it to go to some place by some angle and some distance, or attain a certain speed, but that is the actuator only. If you would now want a meaningful application, then you would want a sophisticated control. So what's control? Control is on top of your basic actuation. So imagine a car that has, or a robot that has to follow the line here. So I am guessing that as engineers, you would have, at least at one point in your life, you must have seen a line following robot. So what is this line following robot doing? So we all know inside this robot car, of course, there are two motors at least, and those two electric motors, they are of course being driven, but what is making it follow the line? That is the most basic control. So at the very basic level, it would be an on-off control that works like this. You have sensors which detect the line. So if you are going towards the left of the line, so you turn right. If you're going towards right, then you turn left. So on off, or right left control. So that is the most basic control. But you can imagine that this would be a very jerky control, just like a newbie driver. If when you first start learning driving a car, so you drive like that. You first go all the way to the left, and then maybe you go all the way to the right, and then you press the accelerator too hard, then you brake a lot. So jerky motions. So that jerky motion is what is the most basic control is. And as you improve your driving skills, then you get a more fine control. And then you know that, okay, if a speed bump is coming up, so you would gradually take your feet off the accelerator and slightly press the brakes. And then after the speed breaker, you gently press the accelerator, and there is a very smooth motion to that. So how is that happening? Ultimately, what you are doing in your head is this control, PID control, proportional integral derivative control, or differential sometimes. So again, in your, I'm sure electrical engineers and mechanical engineers, they definitely read about PID controls in some of their courses. For the other people from other backgrounds, they may not use it directly, but indirectly, I'm sure they will encounter this type of control somewhere. So PID control is a huge improvement over the on-off control, and that gives the any motor control of the precise or smooth control. So we call this an intermediate level control, not the basic, but somewhat intermediate, and also not too advanced. But most of the cases, you will find that in most robotics projects, you will find that the PID control is sufficient to give you a very smooth kind of. And then we will have more advanced control. One example of a very advanced control is this fractional control. And those fractional controls, they are used in very sophisticated operations. So if you are looking to a robotics project, then maybe this PID control is sufficient. So over here in the right, you are seeing is an application, a toy application, you could say. This is called an inverted pendulum. So here you can see that in this inverted pendulum, the goal is to hold these three sticks upside down. So the actuator it can only move sideways. There is no other actuation. But there are sensors that have been mounted here. And what type of sensors? They are called the tilt sensors. They measure how much the bars are tilted. So the kind of sensors that you have in your smartphone. So your smartphone knows if you are holding it horizontally or vertically, and then it accordingly shifts your screen. It rotates your screen. So these are called the tilt sensors. So the same type of sensors are probably installed in these three bars, and based on those three, this motor here, or the actuator, it is just doing this translatory motion and balances that. And that is probably a much more advanced control. But you could do a similar thing using PID control as well. So we have seen that the most basic of things is the actuator, the motor. You are giving it some control signals so that it moves forward, backward, some speed control, and so on. And on top of that, you need to have a control. The purpose of this control is to, for example, have so I think we are experiencing some noise here. So could you please, all the participants, switch off your mics? Okay, so on top of the basic actuation, we have control. And the purpose of this control is, like we saw in the previously, it could be as simple as follow something, follow a line, follow a path, maintain speed, or maintain, in the case of airborne vehicles, maybe maintain some angle of flight, and so on. So this is what we call the basic control. And then on top of this thing, we have the guidance. So the guidance is going from A to B. So this is the purpose of the higher order robots. For example, a missile. So there we could make use of certain more advanced sensors as well. So simple position and speed sensors, they may not do really well. So we would want some more advanced sensors there, plus some other sensors like air temperature or air speed. They might come up because maybe the missile has to move up or down based on the air temperature and speed, so as to maintain some flight characteristics. So that is the purpose of the guidance now. So that is a higher level control. And now you can see that very quickly we are now moving upwards, and the robot or the system is becoming more and more sophisticated. And once we do add some autonomy to it, that means doing something. So we just give it a goal and then it does it automatically without human interference. So that's what we call artificial intelligence. So you can see in this example here, this is the same robot dog from Boston Dynamics. So maybe the goal is start from this point A and come to this point B, and whatever happens in between, you are responsible. So what is happening? So these legs that this robot is using, those legs are, you could guess that they can only do an angular motion. They are not fully rotating. So they are some type of servo motors. So maybe you actually, if you look online, you will find that there are replica dog group robots available which use simple servo motors. And although they are not as sophisticated, but they do a pretty neat job of mimicking it or replicating this motion. So there are servo motors, and those servo motors, there are not just one or two of them. There are actually maybe 16 or 20 of them inside these legs. So each of those servo motor legs, they are actuators, and they are getting signals from the control. Maybe control is simply that to do this back and forth motion in a certain fashion. And that control is getting commands from the guidance that, okay, we have to go from A to B. And then that guidance is further being dictated by AI. So maybe there are there are certainly sensors which are also looking for the obstacles. So for example, when it goes here, it senses an obstacle, then it gives some further guidance to this control unit that, okay, now you have to jump as well. So now the guidance will slightly change the characteristics, and it will say that to the control that now your job is not just to a simple motion, but also jump. And then the control will accordingly translate this command to the actual motors. And this is how it will happen. So the guidance, when it is driven by AI, that's the ultimate goal, that we make robots that can just, we give them a very, very high level command that go from A to B and do it at any cost. Even if there are obstacles or anything, you have to just do it. So you could see another view here, another example here, where this robot is being perturbed by an external force. So you see, neither the actuator nor the control nor the guidance, none of them, they can actually sense that. So this is, they cannot foresee that. So some intelligence, you could say, is built into this control, that if there is something, if there is a perturbation or something that tries to topple the robot over, then there are sensors available. And again, the most common of them is the tilt sensor. So the control, without telling the guidance or AI that I have experienced a kick, it will just try to balance itself using the so there will be a feedback within this simple control and actuator. So that perturbation is probably being handled through this sensory motion. But this kind of obstacle, this is a different one. So that is probably being sensed by the AI using cameras, and AI is telling it to change it. So different type of perturbations could be handled in different ways at different levels of control. So this is what I meant now when I started this presentation. I said that these days robotics is all about actually AI and machine learning and computer vision. Why? Because these three things, they have been sort of matured now. Over the years, past 20, 30 years, we have had enough research going on to these, and making good motors, electronics, and control and guidance algorithms, they are all there. And I'm not saying that the research has stopped there. They are still, of course, making things better and better. But these things, they have sort of matured. But this AI, that is still working in the works. And you can imagine why, because this is still not the solved problem. So if you see this sensor at the top of this, which is rotating, this is a LiDAR. This is a very expensive piece of equipment. And what does it show you? Let's take a quick peek here. If you look at this video here, this is not an ordinary video. This is a LiDAR data in 3D. So this LiDAR in this case is mounted at the top of this car, and you may have to spend some time understanding what is happening. So basically what is happening is, these points that you're noticing, they are not actual images, but they are the distances. So this LiDAR works by giving you the distance in three dimensions for each and every point that it can look at. So using lasers, it shoots lasers, and then it tells you where each and every object that it could hit is at. So this information is extremely valuable in robotics, and because it could help you get a very good sense of the environment. But then this piece of technology, this is relatively new, and right now, if you would want a 3D LiDAR with which is still the cheapest one of them, this comes at a price of 50,000 Saudi riyals. This is the cheapest one. And Tesla is not using LiDARs. Tesla autonomous cars, they don't use this. But Google and Waymo and others, Google and Uber, etc., they are using this LiDAR in their cars. So what is Tesla doing? Tesla is trying to do a similar thing with the images and videos. So that's why I said that images and videos and processing of images and videos through AI, that is now the centerpiece, because now they could do a lot of similar things using images. So even though this camera does not tell you exact position of each and every part, each and every component, it can give you a fairly good idea of where the objects are, where it could hit. So that's why in robots these days, the challenge is not in the control of the actuators or guidance or such lower level stuff, but the focus is now on the high level AI control. And for that, the focus is now on the environment perception, which kind of environment the robot is moving in, where exactly is the robot localization. So again, as we mentioned, that outdoors maybe GPS is sufficient, but indoors there is no such thing as a as an indoor GPS. So indoors is still a problem. So images have taken up a lot of these tasks, and they have actually solved a lot of problems related to this. So that's why in most of these environmental perceptions and so on, images can be, most of these problems, they can be done through image processing. So what does image processing do? The most basic of this task is the object detection. So what is object detection? You just see in the images where different objects are, and we just try to locate them. So this is what a robot would be looking at. So if this is the camera at the front of the robot, so it would know through this information that where it is. Are there too many humans in the vicinity? Are there too many vehicles, and where exactly there are vehicles, and so on. So we are not getting the exact distance information like the LiDAR does, but it does actually maybe a more important job by identifying the objects that are in the picture. And with stereo images, with stereo videos, that means two cameras side by side, we could also detect the distance as well. So another very commonly done thing, or very important thing, is the image segmentation, where we not just identify the objects, but we also do a pixel by pixel job. So for example, the camera at the front of the car is taking this picture, and the output of the AI task is this one. So that's a very neat and clean depiction of what the scene looks like. So there is sky at the top, then we have roads, so they have been color coded in a certain way, and then the vehicles, they are also they have been also color coded, and you see this pothole on the road that has also been identified. So that's the ultimate goal. When we segment the image into different tasks, then this can do a fairly good job of telling the robot how to behave in this environment. So all of that can be done through, if you have only just a single camera in front of the robot and a very good processor and a very good algorithm that could do this job. And we have done pretty good jobs, pretty good research work on that. And it is, although this is an idealistic view, but we have come much closer to this idealistic view. And then of course you could do also very simple human interaction as well. So if you have done, if you have worked with the Xbox controller, the depth sensor, so you must have seen that this technology has also matured a lot. And then one very major problem is indoor localization. So that indoor localization problem has been again solved through this visual place recognition, that your robot inside, it has only the camera at the front, and then it memorizes all those places that it has visited, and then it can localize that where this robot is exactly at in this building in a given map. So this could also be done outside, although outside we know we have GPS, and GPS does a much better job, because collecting images outdoors, that would be just too much work. You will have to collect maybe trillions of images, even if you are just in a single city. But still people do that, and it is a doable job. And another thing, related thing that we could do is odometry. Odometry is the speed calculations and the position calculations. So as I mentioned before, in the motors inside, we already have position encoders available that tell you by how much the motor has moved. But there are a lot of errors in that, and those errors can be fixed if you combine that information by the information that is coming from the images. And that's why images, you see, they are doing a lot of things. You have just one camera at the front of the robot, and it is solving so many problems for you. So it can also tell you how much the robot has moved, by what angle is it, has it maybe moved. If it is an airborne vehicle, maybe a drone, so it could also tell you if the drone has tilted by a certain amount, and so on. So this is an interesting application where they mounted this camera on a dash as a dash cam, and now you see, by extracting information from the video sequence, they can make a sort of a graph like this. They can tell by how much the car has taken the turns, and here they are building the full map of it. And since the outside we have GPS available, so that is not much of a problem outside, but that is of huge importance indoors, because indoor localization is an extremely difficult thing. So, and as we have discussed already, the motors don't give us a lot of accurate information. So we have to resort to these systems, although there are other solutions available as well, but the camera does a very fine job of doing it. So what kind of tools, if you are interested in this, so we have briefly discussed the kind of technologies that go into building modern robots. So what kind of things, what kind of skills you need to learn if you are interested in this topic? So first thing is, of course, the AI, the object detection or machine learning. So the go-to tool these days for machine learning and AI for deployment is probably TensorFlow. And the reason for that is that TensorFlow from Google is investing a lot in that domain, because TensorFlow not only supports the Python, the most favored language of people who are learning just now learning programming languages. So Python is the most favored one, But for when you are looking for speed and other concerns, then you will have to go to C++ and others. So TensorFlow supports basically all of that. And not just that, you could directly deploy your solution onto CPUs, normal CPUs, or if you want some speed, then GPUs, and then even if you want even more speed, then TPUs, which are tensor processing units, which is an advanced form of GPU, you could say. And not just that, maybe you would want to make an app out of it. So why not Android and iOS? So that's why TensorFlow is taking this field by storm. And if you would want to deploy your models or your AI solutions onto various things, so for example, your robot could be making use of full-fledged CPU, which is generally not the case because your robots are smaller. So you will probably be deploying things on smaller scale. So in that case, maybe the Android, it could be running an Android, or it could be running a smaller GPU. So in that case, again, TensorFlow is supported. This is one simple example of how TensorFlow could help you with the process with the detection task. But I think in the best interest of time, let's move forward. PyTorch is another flavor which is probably more driven by the Facebook research group. But you can see that Facebook has a very different goal. So maybe in the robotics area, PyTorch is probably not the right tool for that. So I would advise going with TensorFlow. What other libraries or tools maybe you will need to look into? Of course, getting your own high-end GPUs and TPUs. This is not for training models for AI. For developing AI systems, you need high-end systems. So of course, that is not always possible. So Google has made a cloud computing framework available for you. Some of it is free, which is, and if you want even more computational power, then you could pay it. You can get a subscription version as well. So that is what we call the Google Colaboratory or Google Colab. So you could practice your machine learning or AI tools there. Then OpenCV, which was originally developed by Intel for doing computer vision tasks, simple image processing tasks. But as we have just discussed that now image processing and everything related to computer vision, now this is automatically considered a part of robotics. So that would mean if you are into robotics, that automatically mean that your robot will definitely have a camera installed, because we have already seen that cameras solve a lot of problems. They can help you remove a lot of other sensors. So that's why you could say that OpenCV is almost a required skill for robotics enthusiasts these days. Similarly, MATLAB is doing a lot of good things. MATLAB is providing a lot of frameworks, especially for teaching. MATLAB is quite good at that. But the problem with MATLAB is, of course, the licensing. So if in universities, KU, for example, has a license for that, so we could make good use of that license and do a lot of things there. But of course, later on, when you don't have access to MATLAB, then this could be a problem. Then there is a specially designated library, which is the ROS, Robot Operating System. And although it says operating system, it is not exactly an operating system. It is a library actually, so many of the applications that you saw in the beginning, like visual odometry, for example, or the localization or moving or the PID control, the basic low-level control, the PID one. So all of those things, they have been basically implemented by different people in this library. So this is an open source library and people contribute, and this is a very, you could say, professionally built library which you could use in your robotics project. So there is, of course, some learning curve involved there, a lot of supervisory tasks and data tasks which could come as an overhead. But once you get past those hurdles, then ROS is an excellent tool to build robots, because a lot of stuff is already built by other people, and not just built, but also tested extensively. So ROS is a good way but of course, in smaller systems, smaller microcontrollers, you cannot you cannot incorporate ROS. So in order for ROS to run, you will at least need a Raspberry Pi, which is a small embedded system, or maybe a Jetson Nano, which is a slightly bigger system. So you will need a reasonably sized CPU or GPU for that. It won't run on smaller microcontrollers. All right, so what we did at KU, just to give you some idea of what we can do with whatever limited resources we have. This is one project that we did using a very cheap version of the lidar. It is a 2D lidar. It is not the kind of lidar that you just saw the demo for. So this is a 2D lidar. It does not get a very good job, but it can do pretty well inside neat and clean corridors. So you see this robot is moving around in a corridor inside one of our buildings. So you see after running back and forth for some time, it has made a map of the building. This is a slightly more complicated corridor. So you see initially the robot did not know the map of it, but after just going back and forth, it is sensing the environment through the lidar and it is building the map. So you see by the end of this exercise, it would have made the measurements, made the map, and so you could use such a robot in disaster scenarios. For example, if in case of a building collapse or something like that, you could send the robot inside and it will go inside and do a survey and tell you later on what kind of structure is left intact inside. Second second case study you could say that we did here. This was a joint project between electrical and computer engineering department and the nautical engineering department. So what we did was we built a surface vehicle. So this was done in a workshop in Jeddah. This simple boat or surface vehicle, and then we hooked this up with fishing motors. So these motors, they are used for fishing, and then we hooked this up with an autopilot, which is normally used for quadcopters and flying drones and so on. So you see, we just integrated a few things, then we added some electronics for communication and so on, and alhamdulillah, we were able to do a very fine job. And we tested it on the Faculty of Marine College facility, and we tried the autonomous mode here, and we set this, so both autonomous and manual control. So we set the waypoints going from A to B, for example, on the software, and the boat actually demonstrated that it went from this point A to this point B, for example, and then to another point C, and then it went back. So it was, alhamdulillah, great success. And you see, this was the only chance that we had to take the boat to the sea, and it was the first time, and it worked, alhamdulillah, on the very first attempt. The last case study, not the second last case study, is this one where we, with students again from ECE, they converted a small child's car into an autonomous mini car. So they make use of ROS, which we were just talking about. They implemented this on a Raspberry Pi. Here you can see, and it was able to detect the traffic signs and then change its speed accordingly. And it could also check the stop signs, for example. So when it reaches this stop sign, it will stop there. So again, a mix of artificial intelligence, some ROS capabilities, robotics, and motor control. So this was this autonomous mini car was accomplished. And finally, just 2 years ago, we did this AI NEOM challenge where, alhamdulillah, our KAU team, it came in third. And the idea was, again, to make a robot which will visit places instead of you. So you will be sitting at your home using a VR goggles, and the robot will send you the live video there. And if you are turning your head right and left or up and down, so the robot will mimic your motion, and you will feel like you are actually visiting that place. So this was powered by this Jetson Nano, and it made use of this stereo camera. So it can detect the distances as well as it can give you a very immersive perception. So this was doing a lot of visual perception, which is based on AI. And in starting this semester, inshallah, we are developing some further robots for indoors. So the purpose of these robots are to help with indoor tasks, carry a lot of weight and things which we cannot normally do. So you may notice that we are using the so-called the hoverboards, although they are strictly speaking not hover, they don't hover, but we call them hoverboards. So they are exceptionally good piece of engineering. They can carry a lot of weight, and they have they can go up to 20 kilometers an hour sometimes. So that is good enough for indoor environment, and we can put a lot of weight there. So you see, we intend to use a stereo camera in front. Of course, we cannot get the 50K lidar, so we are trying to use stereo cameras. So and we could do all the processing there, and ultimately we hope to build a working robot, inshallah. So if you want to work on this, of course, a lot of hardware platforms have recently become available. So you can imagine that some 30 years ago, you did not have the luxury of having all of them here. So even 30 years ago, even getting a small microcontroller was pretty hard. You did not get anything soldered neatly like this. You get loose parts, and you will have to solder everything up yourself. And building this was probably a project. So these days, fortunately, our embedded systems, for example, a Raspberry Pi or Jetson Nano, they pack a lot of power, and that's not, again, too expensive. You can get them very cheaply, and they can do a lot of things for you. You can put AI into it. You could control low-level motors in it. You could implement ROS on it. So a whole robotic system could be implemented theoretically and practically on such systems here, using ROS. So what you should be prepared for, of course, a lot of algorithms, design, mathematics, programming, and a lot of your sweat. So engineering, as I keep on mentioning in every lecture that I give, that if you're not tired, you're not doing it right. So that's the end of it. I'm afraid we don't have much time left for the question and answers. So if you still have questions, you may ask me through my email or in whatever time we have left here, so we could listen to your questions. Thank you for listening.
Thank you, Dr. Muhammad. It was an interesting topic. So that's it. There is the attendance link in the description, the chatting.